What is the role of orbital mechanics in weather satellites? Imagine trying to watch the weather across the entire world from space. How do these satellites stay in the right spots to give us accurate data? That's where orbital mechanics comes in. It's the science that explains how objects move in space, especially around Earth. Whether satellites need to follow specific paths to do their jobs well. There are two main types of orbits they use: geostationary and polar orbits. Geostationary satellites orbit about 36,000 kilometers above the equator. They move at the same speed as Earth spins, so they stay fixed over one spot. This means they can watch the same large area all the time, which is perfect for tracking storms and hurricanes as they develop. To stay in this position, they balance the pull of Earth's gravity with their orbital speed. This balance is a key idea in orbital mechanics. If they go too high or too low, they drift away from their spot. Polar orbiting satellites fly much closer to Earth, usually between 700 and 850 kilometers above the surface. They pass near the poles and scan the entire planet over time. Because Earth rotates underneath them, they can cover all land and ocean areas. These satellites orbit roughly every 98 to 102 minutes. They often follow Sun's synchronous paths, crossing the same point on Earth at the same local solar time. This helps keep lighting conditions consistent for imaging. Orbital mechanics also helps scientists adjust satellite paths. By changing altitude, inclination, or speed, they can make sure satellites gather the best data. For example, polar satellites provide high-resolution images and detailed atmospheric data. Geostationary satellites give continuous, real-time views of weather systems. Both types depend on precise calculations to stay in their orbits. Weather satellites use these principles to stay in the right place for their tasks. Geostationary satellites give us constant updates on fast-changing weather, while polar satellites give detailed global coverage. This balance of forces keeps satellites stable and working properly. They measure temperature, humidity, wind, cloud cover, and more, all thanks to the careful planning based on orbital mechanics. Advanced satellites like those in the METHOP second-generation series relying on these principles to stay in the right orbit. They help create three-dimensional atmospheric profiles, monitor ocean winds, and observe surface conditions. All of this depends on maintaining their orbits as predicted by orbital mechanics. Without it, these satellites couldn't provide the accurate, timely data we relying on for weather forecasts and climate studies. So, in simple terms, orbital mechanics is the backbone that keeps weather satellites in the right place to do their important work.